So far, our discussion has been confined to finding the potential after first finding the electric field using Gauss's law. Sometimes this is not suitable to do. For example, suppose we want to find the potential at point P, which is the origin in this coordinate system. And let's suppose you have a semi-infinite rod, a rod that starts at x equals d and goes off to x equals infinity. Now observe the coordinate system is x is positive to the left. So how would we find the potential? Finding the electric field first is not a good option because finding the electric field is just as hard as finding the potential directly. So what we're going to do is we're going to take the approach of using calculus directly. So if you think about any portion of the rod, it's got a charge dq, and that portion of the rod has also got a length dx. So we can relate dq and dx through lambda by means of the definition of lambda. Lambda by definition is the rate of change of charge with respect to x, as we saw in week 2 of this course. So we can simply use the old methods and find out dq in terms of lambda and then find the potential directly. It would be very helpful to have an expression for the potential of a point charge. So I'm going to develop that off to the right side and then I'll come back to deal with this problem. So let's talk about the potential due to a point charge. For this calculation, we can in fact use Gauss's law because there is going to be spherical symmetry. So let's suppose you have a single point charge q, and for the sake of this calculation, let's assume it's positive. Now the left-hand side of Gauss's law will have all the hallmarks of spherical symmetry because you're going to have the electric field and the dA vector parallel to each other no matter where you go on the Gaussian surface S, which is a sphere concentric with a charge. So the left-hand side of Gauss's law will go as always. The flux phi E closed will end up being, which is equal to the double integral oriented over the surface S of E dot dA will be equal to the integral E times dA times cosine of 0 degrees. I can pull the E outside, so that's E as a function of R, and then the double integral of the area of a sphere, well, that is just 4 pi r squared. So that nice 4-step process gives us the left-hand side. The right-hand side is just the charge enclosed over epsilon naught, which in this case is equal to Q. So immediately I get the electric field as a function of R. It's just the Coulomb constant K Q over R squared. What I've done here is when I divide by 4 pi, I'll get 4 pi epsilon naught, which I've made equal to 1 over K. So that's the electric field, and I can write that as a vector also. So I've written out the electric field for all of space. Now once you have the electric field for all of space, you can actually find the potential difference between any point, let's say R, because the Gaussian surface radius is R, and infinity. So that's a pretty short distance to infinity. Now what I'm going to do here is to choose a path of integration from this Gaussian surface all the way to infinity. And that'll be our potential difference. Remember, the master equation for potential difference is delta V equals minus integral, the initial value is R, to infinity of E of R. Now mind you that E of R and dr are parallel in this case. E of R points outward to infinity and dr also points out to infinity like that. So E and dr are parallel, so that's going to be E of R times, there's no vector there, dr times cosine of 0 degrees. And now I'll just substitute for this. I'll get negative kqr constants, integral r to infinity dr over r squared. Well, the integral of 1 over r squared is negative 1 over r, which cancels with a negative sign here. So I get 1 over r from r to infinity You've probably seen this calculation already 3 or 4 times by now. On the left side, this is v at infinity minus v of r, and all that's equal to 1 over infinity, which is 0, minus 1 over r times kq. I forgot the kq here. It's still there. V of infinity is 0 by convention, so that gives me negative v of r equals negative kq over r, and cancelling out the negative signs, I get the very famous expression for the potential due to a point charge. Now this is going to be our bread and butter in this method. What's true for points is also true for infinitesimal line elements. And that's going to be our philosophy here. Even though the way I've drawn it, that doesn't quite look like a point here, we're going to assume that it is, because in the sense of calculus, it is. So on this side, what I'm going to do is I'm going to say the potential due to the charge dq the point charge, I'll put it within quotes because it's certainly not a point, at the point P, what is that going to be? That's going to be given by dv equals k dq divided by r. I'm just replacing q here with dq, and r is the direct distance between the element and the point in question. In other words, this distance here. That distance there is r. That distance is just x, because this lambda x, by the way, is beta x to the minus 2 with respect to the coordinate system drawn here. So that distance is just x. All right, now I've found what dv is. All I have to do now is substitute for dq, which is right here. So let me do that in the next step. dv equals k times lambda times dx divided by x. Now you observe that lambda is beta x to the minus 2. So beta x to the minus 2 divided by x is k beta x to the minus 3 dx. Well, that is the infinitesimal voltage dV due to the charge element dq of width dx. The complete voltage is got by the principle of superposition. So the complete voltage is the integral over all these dv's from where the rod begins. The rod begins at x equals t, and where the rod ends. Well, the rod ends at x equals infinity. So let's perform this integral. K and beta are constant, so I'll pull them out. So I get the integral from d to infinity x to the minus 3 dx. Well, that's easily got by using the standard formula for integrating polynomials. So that's x to the minus 3 plus 1 divided by minus 3 plus 1 from d to infinity. Let's see what that would be. K beta, and this is negative 2. So I'll write this as negative k beta over 2. And here this is x to the minus 3 plus 1, which is x to the minus 2, which I'll write as 1 over x squared between the limits d and infinity. So let's evaluate this now. It's k beta divided by 2. Now if you were really being rigorous in the calculus sense, you'll write this as an improper integral. So I've not been doing this, and I feel a little bit guilty about it. So I think I'll do that for once. So that's going to be limit b goes to infinity 1 over x squared d to b. Okay, now I'm being rigorous. So that's negative k beta over 2, limit b goes to infinity 1 over b squared minus 1 over d squared. Well, the limit of 1 over b squared as b goes to infinity is 0. So that gives me my answer, which is negative k beta divided by 2 times negative 1 over d squared. And if you take the two negatives together, I get k beta over 2d squared. So that's the answer. Now let me point out a wrong way to do this problem. There is a wrong way to do this problem, and I also want to point that out so that you don't do it. So I'll make sure that I mention that this is wrong because I don't want you to think of this as a shortcut. It's not a shortcut. It's a wrong cut. So I'll write this wrong method. If you're strapped for time, students end up using this wrong method, but you won't have the time issue, hopefully, in this exam. The wrong method is students just find the total charge and use the point charge formula. Let's see why that would not work. The total charge, Q, is the integral of dq from d to infinity. Well, the integral of dq is lambda dx, which is beta x to the minus 2, because lambda has just got that, beta x to the minus 2. So let's write that. Integral d to infinity, beta x to the minus 2 dx. And if you perform the integration, that's x to the minus 1 over minus 1 from d to infinity. And I won't go through all this. The answer will just end up being beta over d. Now, the student or whoever does this thinks, well, I'm just going to put this there. V of r, so the v at the origin at point P is going to be beta k times beta over d. Well, what to use for r? Which, you probably end up using d. Well, the problem with using d is that it's k beta over d squared. It's twice the value you got there. Then maybe you say, well, I should probably have used some other distance, not d. It turns out the correct answer is got when you don't use the distance d, but when you use the distance 2d. Now, that 2d, how does that come about? Well, the real answer is it comes about like this. But for those who are curious, I would like you to explore the following question. What secret physics lies behind the magical distance 2d? Basically, what's happening here is you're getting the same answer by the wrong method as the correct method by finding the charge first, and then somehow, if you know where to put that total charge, you will have come with the same answer as that. But to know where to put that total charge, you need to think pretty deeply. So I would like you to explore it. For those who don't get it, don't worry about it. The right method is right there. And that's all I want you to look at. I don't want you to study the wrong method to any degree of detail.